Hello everyone, welcome to this presentation. In this video we are going to talk about DC inductors. We will see an introduction, then the basic equations that we need to analyze an inductor. We will talk about the total permeability and the differential permeability. Then we will talk about the effective or differential inductance, how to calculate the effective inductance, and finally we will see an example of calculation using WinPython. Let's start by defining what is a DC inductor. A DC inductor, also known as a choke, is a common device usually employed in power electronics applications and also in telecommunication applications. DC inductor is commonly used as a filter, and usually the waveforms that we have in a DC inductor are like this one shown here in the slide. We have a DC current circulating through the inductor, and this DC current has superposed an AC component, as we are expressing here with this equation. Also, we have a voltage across the DC inductor that, of course, is not going to have any DC level, but what we have is an AC component of the voltage across the inductor. If we look at the inductor and the equations that we have, we know that the voltage is the inductance times the derivative of the current with respect to the time. So in this case, we can substitute the current in this way. So at the end, the voltage is going to follow this expression here. The voltage is equal to the AC component and is equal to the inductance times the derivative of the AC component of the current with respect to time. The question here is, what is the value of the inductance that we have in an inductor like this, especially in applications in which the inductor can operate in the saturation region of the BH curve of the magnetic material. We have here below an example of an application of a DC inductor in a buck converter. In the buck converter, we use this inductor here together with the output capacitor in order to filter the voltage across the output. So, as we know, the current is going to have a DC component with an AC component. In this case, the AC component is a triangular waveform like this one. And the voltage across the inductor is a square waveform like the one shown here. The maximum value is Vi minus Vo, and the negative value is minus Vo. So we can see how, if we take the derivative of the AC component of the current here, which is the triangular waveform, then we obtain this square waveform for the voltage across the inductor. Other applications of DC inductors are in telecommunications applications and also in audio amplifiers, in which these DC inductors are used to bias the amplifier at the desired DC operating point. Let's revisit the operation of DC inductor. As we know, a DC inductor can be represented physically like this. We have an equivalent toroidal core with a given length, a given area, and a given air gap, and we have a winding with a number of turns n. If we look at the BH curve of the material, we are going to have a DC level of the magnetic field intensity H, which is proportional to the DC level of the current, and also we have an AC component of the magnetic field intensity, which is also proportional to the AC component of the current. Then we are going to generate an equivalent value or a given value of the magnetic flux density B and a given value of the AC component of the magnetic flux density. Usually a DC inductor is going to operate here in this linear region, but in this presentation we are interested on what is going to happen if we move this DC operating point close to the saturation part of the BH curve. In this case, we know that the inductance is going to decrease because we have seen many times these curves in the manufacturer's datasheets in which they are showing the inductance as a function of the current, and we know that we have a range here with constant inductance, but when we increase the current and go close to the saturation region, the inductance is going to decrease. Here on the left we have the basic equations that we have to analyze the behavior of an inductor. We have the magnetic flux, which is equivalent to the magnetomotive force divided by the reluctance. The reluctance consists of two components, the reluctance of the core and the reluctance of the air gap. And we have here also the well-known expressions here for the values of the reluctances, and also we know that the inductance that we are going to have is the flux linkage divided by the current through the inductor. So we can use these expressions here. The flux linkage is the number of turns times the flux divided by the current. So finally we can get this expression here, the number of turns squared divided by the reluctance. Now the questions that arise here are the following. Here we have a reluctance which is equal to the length of the core divided by the permeability divided by the area. But what is the value that we have to use here for the permeability of the material? The other question is if this equation here is really providing us with the correct value of the inductance that we need for the differential equation of the inductor. And the final question is how can we obtain this curve here that gives the value of the inductance as a function of the current through the inductor. To answer these questions, let's review first what is the permeability of a given material and the two basic definitions of the permeability of a magnetic material. When we are operating at a given point of the BH curve like this one here, we can define two different types of permeability. The first one is the ratio between the DC level of the magnetic flux density and the magnetic field intensity. So we have this definition here that we are going to call the total permeability of the material. We can also define what is called the differential permeability of the magnetic material. So the differential permeability of the material is defined as the derivative of the magnetic flux density with respect to the magnetic field intensity. So if we make a perturbation in the magnetic field intensity, then we are going to obtain a given perturbation of the magnetic flux density, and these two both quantities are going to be related, as it is shown here in this expression, by the differential permeability of the material. Then, in order to analyze the behavior of an inductor when it is operating in the saturation area of the magnetic material, then we need to obtain first expressions for these permeabilities, the total permeability and the differential permeability. There are different possibilities. In this presentation, we are going to use the Brouwer's fitting that provides the values of the total permeability and the differential permeability as a function of the magnetic flux density, as shown in these equations here, in which K1, K2, and K3 are constants that depend on the type of material. For example, for the N87 material, we can use these values here shown in this table. Let's see now what is the relationship between voltage and current in a given inductor like this one here. We can take a look at the BH curve of the material, and we know that if we have a given value of the current, then we know the value of the magnetic field intensity, H, which is proportional, so we can go to the curve and obtain the value of the magnetic flux density, and then from the magnetic flux density we can obtain the magnetic flux multiplying by the area the equivalent or the effective area of our core. So from this we could obtain an inductance that we are going to call the DC inductance LDC, which is the ratio between the flux linkage over the current. So we will have this expression here, the number of turns times the flux divided by the current, and this obviously is a function of the current that is circulating through the inductor. So from here we could say that here we have a value of an inductance, so in principle the voltage will be this value of the inductance times the derivative of the current with respect of the time. But this is wrong. This is not the value that we need to use in this differential equation. So let's investigate this a little bit further with these other equations here. What we know for sure is that the voltage across the inductor is going to be the derivative of the flux linkage in time. So from this equation here, we can obtain that the flux linkage is the DC value, this inductance, this value of the inductance that we have obtained, times the current through the inductor. But this value of the inductance depends on the current level in a general situation close to the or inside the saturation region of the VH curve. So we have to take derivatives like this: LDC times di dt plus the current times the LDC dt. So if we go further, then we can do like this here. We have the same expression, but here we are taking first the derivative of LDC over di and then times the derivative of the current with respect to time. So then we have here these two di dt's, so we can express this equation like this, in which we have a given value which has also units of inductance here times di dt. So this value here is what we can call the effective inductance of our inductor. So we can see that the effective inductance, as we are showing here, is the value of LDC as defined in this previous equation, plus the current times the derivative of the DC inductance with respect to the current, which is also a function of the current which is circulating through the inductor. So at the end we can say that this is again the differential equation that we have to know the behavior of the inductor, which is the same as the usual one, but when we are operating in the saturation area we have to use this value of the effective inductance that is going to depend on the current level. And also note that this equation here with this definition for the effective inductance is valid not only for DC inductors but for any inductor that operates in the saturation region of the VH curve. Now let's see what happens when we have a DC inductor in which we have a DC current circulating through the inductor, an AC component of the current superposed to it, and then we have the AC voltage across our inductor. As we have seen, the voltage can be expressed as the effective inductance, which depends on the current times the di dt. So if we add perturbations to this equation here, we can say that the DC level VO, which is going to be 0 plus the AC level of the voltage, is equal to the effective inductance evaluated at the DC point plus the value of the AC component times the derivative of the total current. And since the effective inductance as a function of the current is going to be a continuous curve, we can approximate the value at the DC level plus the perturbation by the value of the effective inductance at the DC point. And therefore, because the derivative of the DC level is 0, then we can obtain finally this expression here, with the relationship between the perturbations of the voltage and current in the DC inductor. Here we can call this, instead of effective inductance, because we are working with perturbations, this could be called the differential inductance. So therefore what we are getting here is that the differential inductance is approximately equal to the effective inductance. And this is going to be true as long as the perturbation of the current that we are injecting into the DC inductor is small enough compared with the DC level of the current. Now let's see the process to obtain the differential inductance of an inductor. First, as we have seen before, we can obtain the DC inductance using this expression here. At the end is going to be the number of turns squared divided by the reluctance. And because this is the inductance at the DC operating point, the reluctances are going to be obtained like this. The reluctance in the core is obtained by using here in this expression the total permeability of the material, which is given by the ratio between the DC level of B and the DC level of H. So from this expression we can obtain this curve here in red that is going to provide the DC inductance of the inductor. And then from this curve we can obtain the differential inductance by using the expression that we have seen before. As we can see, this derivative is going to be always negative, so the differential inductance is going to be lower than the DC inductance. So in this way we can obtain this curve in blue, which corresponds to the value of the differential inductance. And we have to note that if the level of the current is low, then we will be operating in the linear part of the VH curve, where the total permeability is approximately equal to the differential permeability, and therefore the differential inductance will be approximately equal to the DC inductance. This corresponds to this part here in the characteristics in which both inductances are equal. The problem of calculating the differential inductance using this expression here is that sometimes it can be difficult to obtain this derivative with accuracy in the mathematical analysis. So let's see a better way of obtaining the differential inductance. For this, we can see that the permeability, the differential permeability, is the relationship between the perturbations of B and H. So we can say that the perturbation of the magnetic flux density is equal to the differential permeability times the magnetomotive force, the perturbation on the magnetomotive force divided by the length. So following with this reasoning, we can say that the perturbation on the flux is equal to the perturbation of B times the area, and then we can get this expression here, and at the end we can obtain an expression like this one, in which the perturbation of the flux is equal to the perturbation of the magnetomotive force divided by this quantity here that we can see as a reluctance, which is the effective length of the core divided by the differential permeability and divided by the area. So we can define a small signal reluctance R in this way, and with this we can say that the perturbation on the flux is equal to the perturbation of the magnetomotive force divided by the small signal reluctance. Now, in our DC inductor, we can apply the superposition law, assuming that the AC component of the current is going to be much lower than the DC component of the current. This is not a very restrictive condition because usually DC inductors are employed as filters, so the AC component is going to be much lower than the DC component, and also because, as for example in the case of DC-DC converters, we want to have low losses in the magnetic material, so it is important to have a small amplitude of the AC component of the magnetic flux density. In this way, we can analyze on one hand the DC behavior of our inductor, and then we have all these equations in order to calculate the DC level of the flux and the DC value of the inductance. And in this case, we need to use the total permeability in order to calculate the value of the different reluctances. On the other hand, we have the AC component of our DC inductor, and for this we can use exactly the same equations, but in this case we have to use the small signal reluctances. And in order to calculate the value of the different reluctances, we need to employ the differential permeability of the material. And with this we can finally obtain the value of the differential inductance, which is to be used in the differential equation of the inductor. So with this, we can finally see the process to obtain the value of the differential inductance. We are interested on obtaining the value of the differential inductance as a function of the DC current that circulates through the inductor. So we have seen in the previous slide this expression here for the differential inductance, the number of turns squared divided by the small signal reluctance, and the small signal reluctance has this expression here in which we have the differential permeability, which depends on the magnetic flux density B. So we can see here that with this equation number 1, we have an expression in which the differential inductance is a function of the DC level of the magnetic flux density B. So we need to know the DC level of the magnetic flux density for each level of the DC current that circulates through the inductor. For this, we can use the DC component of the flux. Using this expression, as we can see here, we can obtain at the end the DC flux level as a function of the magnetic flux density and also as a function of the DC current that circulates through the inductor. Because the magnetic flux density is the flux divided by the area, we finally obtain this expression in which we can obtain a relationship between the DC levels of the magnetic flux density B and the DC current through the inductor I. So by solving the system of equations 1 and 2, we can finally obtain the differential inductance as a function of the DC current through the inductor. The easiest procedure that we can implement is as follows. We first choose an array of values for B, for example from 0 to 0.5 Tesla in steps of 0.01 Tesla. Then, using equation 2, we can directly calculate the value of the current that we are going to have for each value of the magnetic flux density B. Then, using equation 1, we can obtain the value of LD for each value of the magnetic flux density and also for each value of the DC current circulating through the inductor. So finally, we can plot the differential inductance as a function of the DC current through the inductor. Finally, we are going to see an example as shown here. We are going to use this core, an EF25. We have these dimensions here for the core, and then we are going to implement an inductor with a number of turns equal to 80 and an air gap length equal to 0.5 millimeters. So we have these two equations, 1 and 2. The first one is to provide the value of the differential inductance as a function of the DC value of the magnetic flux density, and the second one that provides the value of the DC level of the magnetic flux density as a function of the DC current circulating through the inductor. Then here we can see how to implement this in WinPython. We have in this first part the importing of the different functions and modules. Then we have the definitions of constants and the parameters of the inductor and also the parameters corresponding to the pH curve of the material. Then we define here the different functions that we need, the total permeability as a function of B, differential permeability, the differential inductance as a function of the B, and the value of the current, of the DC current, also as a function of the magnetic flux density B. Then here we define an array for the magnetic flux density that goes from 0.01 Tesla up to 0.52 Tesla in steps of 0.01 Tesla. So here we define the arrays that we need, one for the DC level of the magnetic flux density, another one for the DC inductance, the other one for the differential inductance, and for the DC current through the inductor. So here in this loop we are doing all the calculations corresponding to the differential inductance, then the DC current through the inductor, and finally the DC inductance of the inductor. Then we are printing all the values here, and finally we are plotting the inductances as a function of the DC current. Here the DC inductance, and here with this other command here the differential inductance. Both of them are going to be expressed in millihenries. Here we have the WinPython environment with the script that we have just seen, so we can now run the program and see the results. Here on the console we can see the different values that we have plotting corresponding to the 4 arrays, and then we can go to plots and see the corresponding plottings. So in red we can see the DC inductance of our inductor as a function of the current level, and in blue we can see the differential inductance. So we can see how both inductances are almost equal up to a current level of 1.5 amperes. After that we are entering on the nonlinear region of the pH curve of the material, and then we have different values for the DC inductance and for the differential inductance. If you are interested on this topic and would like to have more information about it, please take a look at the content of my book Inductors, Variable and Controllable. Well, this is all today in this presentation. Thank you very much for watching. Please let me know your comments, and I hope to see you in the next video. Goodbye now.